University, and today's my topic is photoplethysmography. This is also topic of my dissertation, will be topic of dissertation. And so I will talk about first about the plethysmography. What is plethysmography and other types of plethysmography, and then photoplethysmography. This is the topic and main topic, and then the applications of photoplethysmography and artifacts, and some current research which is going on in China and in Russia, and then the future of the photoplethysmography. So what is plethysmography? You can see that this word is from Greek language. Plethysmo, it means increase, and graph means record. So it's like it's technology to record the change of volume, increase the volume or decrease the volume. And so the top of plethysmography mainly have these four types. The first is mechanical. The second is electronical. They use impedance, and the third one is called strain gauge. Yes, and the final one is photoplethysmography. So this is a typical sample of application of mechanical plethysmography. It's this device is used to measure the volume of your lungs. This is a sealed box, and the person sit inside, and this machine, this person can get oxygen or air from this tube, and so when the when he do this, so the volume of his body decreased. So this box can let the air into the box, and then the entrance will be closed, and then this guy will be asked to do the deep breath, breath deeply, and because the whole box is sealed, so when the guy do the deep breath, his volume of the body increased, and so the volume of the air decreased in the box. So that is what the pressure of the air to the box increased. So people can measure the pressure to the box, and then they can calculate the difference, the change of the pressure, and finally to calculate out the volume of this guy's lungs, the volume. And then the electrical, I don't have the picture. It's now I know one university is doing this. It's university in St. Petersburg in Russia. It's called the National Research University of Informatic, Technique, Mechanic, and Optic. So it's almost like optical mechanical university in St. Petersburg. They are now making a small device, portable device, to put 3 detectors here, here, and here, like the 3 edges of the heart. And then when your heart pumps, the volume of the heart changes. So because the volume of the heart changes, so the impedance from this point to this point, or from this point to this point, also changes. So they can detect this change of impedance, so the electrical voltage also changes. Then they can know the volume of the heart, the change of the volume of the heart. So this is electrical way of plethysmography. And then the strain gauge is this is it. So they put this rope, for example, around your leg, and make it be tied, like make it be fixed on your leg. And when you're so with the movement, with the pumping of your heart, the volume of or the diameter of your VIN increased or decreased, increases or decreases. And in this rope is water, which in which the electricity can go through. So so when the diameter of the wing increase, the rope will the length of the rope will be
Expand.
yes, and then there is some characteristic in this rope. The usually liquid rope in these ropes will change, and then they can get the parameters which is changed, and then they can know that the diameter of your wing from this change. And the final one is a photon. It's like this. So this is yesterday. You have already saw this equation. So there must be some scattering, so we need to think about it. But from here, we don't need to pay more attention on it, because for now we don't need to make the result be very accurate. So we can just consider about this, and this is the picture. We can see from here to here is almost it's like linear, in a linear way. And you can see that alpha is the coefficient of absorption, and this sigma is the length, or how long the light goes through our tissue, and also our vessels. So this is the picture. You can see this is our finger, and this is the vessel. Our vessels. So we consider it as one vessel, but there are many, so we consider it as one vessel. So when your heart bumps, when your heart expands, then here there will be less blood, and when your heart, the volume of your heart decreases, then the blood will be pushed out of your heart, so here will be more blood. And because the tissues absorb certain amount or certain intensity of the light, so we don't need to consider about the tissue stuff. We just need to think about how many intensities the blood absorbed. So with this, we can see that the absorption is less than this stage. So according to this, we can get the changes of the volume of blood here. And so the picture will be like in this style. No, it's another program. Yeah. So it will be like in this style. You can because this means that the intensity is very high. It means actually, let me think. Well, yeah, this means the intensity is high, and the intensity of reflected light, or maybe transmitted light, because the light can transmit it through your finger, is high, and this part means your blood is a lot, or it's like it's the change of the graphic according to the change of the volume in your volume of the blood in your finger, and so we can change to. So let's continue. That graphic is like waves, and that waves change according to the volume, the change of the volume. And so we have two types of like this sensor. One is called one is transmitted, and another is reflected. But reflected, there is no photo, I think. So this is transmitted. It's like here is the LED, and here is the detector, and well, this is transmitted. And reflected way is move the LED to here, or move the LED and the sensor in the same plate, like in the same platform, if this is the railway for the train. And so this is I think you all know the why. Okay, it's okay. It's not very important. So this is the ECG graphic, and this is the PPG graphic. So you can see that there is some association between these two graphics. So according to this, it is possible for us to calculate from your heart to your finger the blood flows go how fast. Because when your heart pumps, there will be a pulse wave come out, and you can use the PPG to get this pulse wave, and you will calculate out how long it will take. And also for this part, you can see there is a little bit of peak here. So for young people, this peak is very obvious, but for old people, this peak almost we cannot see it. So it's also can be used to in general to determine that your like cardiac system is healthy or not. And so the applications, so it's non-invasive diagnostic, and we can see we can measure the blood flow, like the pulse wave in the capillaries, and also we can define some functional diseases. Do you understand what is it? Functional diseases, especially for some
what function is affected? Blood oxygenation.
Yes,
response.
it's very interesting thing. So we are all like medical students, right? Sort of. So okay, it's no problem. It's usually for male diseases, male functional diseases, like sexual distribution, unfunctional, something like that. Yes. So I want to show you.
Should I remind you that this is a computer now? So
Yes, I know, but my that's copied, printed out from a Russian company. It's called Plus. It's the biggest company of laser technology, and they also have their own institute, and they also have their own graduate school, and they cooperated with the Russian government. So they make this thing to make some parts of man be functional again, and so that this is the trick. And you see that after the treatment, they took the PPG signal from this part, and then they said that there is some difference between these two pictures, but I cannot see any differences between these. So it is like scientifically it's like it should be some difference between like before the treatment and after the treatment. So it shows that the blood flow and the condition of the blood flow in this part just beneath the skin. Yes, so we can use it in that way. And also in China there is a hospital wrote a article about it. They said that so sometimes it's a psychological function, and sometimes it's really that man got a disease. So they can use this to make sure that he got ill, or it's a psychological reason. And so that is the reflected way, and this is the scheme of the device. So this is amplifier, because the signal we get from the photo detector is very low, so we need the amplifier, and then filter, and then amplifier again, and then we use the PC to make some signal processing, and then finally we can got the two signals here. AC DC is nothing about electronic current. It's DC signal. It's like it's a signal from the reaction of your tissue to the laser, the absorption or reflection or scattering from your tissue, and the AC signal is the signal from your blood, which is caused by your blood.
DC is the average amount of light passing through the finger.
Average?
It's the average, the continuous, and
yes,
the AC is on top.
DC should not be changed, yeah, only AC changed. Okay, so from here we can see that it's okay. So there is association, and okay, so there are mainly three types of artifacts. So the first is electrical noise. For example, there are some filters. If we use a hardware filter from the hardware, then there must be some noises. And also sometimes if you use that device in front of the computer, the screen will also affect the detector. And second is nature light, so it's easy to understand. The final one, the first two one is easy to avoid, or easy to decrease the effects. example, my supervisor made a new type of detector, and he used like a metal box like a metal container to put the sensors and the lasers in it, and it works. Like for example, the electronic noises decreased, and but it's still not enough because the most important is motion artifacts. So what is motion artifacts? So that's it. So usually we have this signal, but if we cough, or we shake our hands, or we do some sports, it will cause these artifacts. Like it will make the signal be like totally unreadable. Like yes.
Let's try it.
Okay, let me find one. Here's the artifacts. So this is what I got some data from a sanatorium when they do some massage to the face, and the doctor wants to know that her massage is really useful or not. Like it can really make the blood under your skin be active again or not. But honestly, I cannot see any differences, but I still didn't tell her. Like for example, yeah, you see, here is the artifacts, and also you see the wave is like up, down, up, down, up, down, and because not the patient, the one who is taking massage, she was lying on the bed, and like she maybe had some little motion, and the hand of the doctor like makes some motion. Yes, and for this also the same, you see here, up and down. It's very, oh yeah, and you see here, it's a artifact, and it's motion artifact. And so it's still a good signal we got, but there are even some, for example, I didn't use that detector to do anything. I just wave it, and it still gets some signal like this thing. I don't know why, but it's yeah. And so this is the biggest problem. There are some ideas to decrease it, like oh, right. Okay. Yeah, so we have some ways to decrease the artifacts. For example, we can change the wavelength of the light. We can change the wavelength to the light which can be absorbed by the blood like more heavily. For example, maybe the green light. And then it is supposed that we can get a signal which has a higher or bigger amplitude. And then with the higher amplitude, it means there is more informatic inside. So if we use some signal processing, it will not damage the original signal too much. The second is use I don't know how to say big data. It's like we can make a storage into the device, and we can save some results from different people, and we use these people do some mathematical stuff and processing, and we can know that usually the wave should be in which automatically erase the artifacts, motion artifacts. And the third one is very popular. I found a lot of articles about it, and later there is a photo to show it. And then the fourth way is what I will do next month actually when I come back to Russia. It's use the signal processing technology. So for example, it's not for example. The motion artifact is like a noise. So there are many methods in signal processing to decrease the noise, to erase the noise, to delete the noise. So it's like I have two microphones, and I'm speaking and you're also speaking. What you said is like noise to me, so I can use some signal processing technology to delete your voice and just save my own voice as well. So I think it can be worked. Yes. So this is with the accelerometer. It is made by MIT laboratory in a lab in MIT in America, and they add a accelerometer in this device, and then they do decrease the artifacts, but I still think it's not very good enough, but it's really a way to do it. Yes, and so about the research here, like in China, usually they do some clinical way, like they got some devices from Europe or from Russia or from America, and they use it in hospital because in China there are a lot of people, so there are many samples. So they get a lot of samples and finally do some research on it. And so there are many, like by using photoplethysmography, which diseases we can detect it. So there is one is very interesting. It's about surgery. Like usually they use that laser Doppler device to detect the oxygen in the blood, and also they use some other device, I don't know, to detect whether you are sleeping or not. Like there are some, it's very seldom that sometimes patient will, they are sleeping but they are still waking, like they still wake up, like actually they are not sleeping, but they are sleeping. Technically they are sleeping. Well, they have their conscience. They know that the doctor is cutting their belly or do something, and they feel pain. This is the most important. They feel pain, but they are sleeping. They cannot move their fingers because some part of their brain is unfunctional. And so they use the PPG to detect it, and they figure out that by using ECG or some other they use some usual devices, they can know that that person is asleep or not, and they can use PPG to see that their sleeping is deep enough, or they still conscious, like they still have conscious or not. And then in Russia, so in my university, they are focusing on, we are focusing on the motion artifacts, and another university they are doing like from macroscopic field, for example, like this. It's what they did like 4 years ago, but they have abandoned it because only little hospitals use it. It's used to detect the vein in this arm. It's healthy or not. So there are, you can see there are 4 laser and laser detectors, and so it can make a laser circle on your arm, and so from this part they screw the arm and make the arterial still working, but the vein is not working. and then they suddenly release the belt, and so the blood can come back to the vein again, and so this thing can these four detectors can detect the change of the volume of the arm, like because in vein there was no blood, so the volume was smaller than the volume which in vein there is blood. You understand me? Yeah, so they're doing this. They are not doing this. They have abandoned it, they said. But they said if I want to go on like PhD study to their university, they said we can restart again. But they said you need to prepare that no one wants to buy your device. I said okay, let's start a new topic. Okay, so according to this morning's lectures, this device can, or this technology can also be combined with the laser Doppler device, can combine with each other, and so Doppler is detected changes of frequency, and this one is detected changes of intensity. So it can, I think it can be detected in the same time. So we can combine these two devices together, and so it means in the future that we only need the very small devices, or even we only need to use the mobile phone, and then we will know the oxygen percentage of oxygen in our blood, and our pulse rate, and our system, cardiac system is healthy or not, like this, and then. And so in the future we can use in space, like put that stuff in like spaceman that suit. Yes, and about first aid is very good because the doctor don't have to take a big box. They just need to take some small devices, and then they can know a lot of information from the patients. And also surgery, just as I said, that it will be able to detect this patient is still have conscious or not. It will decrease the dangers that the patients get, like pain. It seldom happens, but it's still better not happen anytime. Okay, thank you. And thank you. Maybe any questions or no questions?
Very interesting. One of the interesting things about the photosmography and microcirculation in general, in terms of general health, is the frequency with which it goes up and down. So obviously there is the heartbeat.
Yes,
and this
yes,
is about approximately once per second, 1 hertz.
Yes.
But there is also a lot of other vasomotion that is happening. So
Yeah.
about once every 3 seconds there is a change due to breathing. Because the breathing is putting some pressure on, you can actually do a Valsalva maneuver, which puts pressure. If you hold your breath and push against your breath, you are squeezing a vessel, maybe a vein. The medical people can explain. But then you see a change. And maybe the most interesting one is the vasomotion that happens about once every 10 seconds, because this is related to endothelial function. So a healthy endothelial function, you will see this kind of activity once every 10 seconds.
So it
approximately 0.1 hertz.
So it is needed. I cannot just like.
Well, if your filter is filtering out 0.1 hertz, then you don't see it, of course. You have to be careful. So, but if you don't do that, then you can see this 0.1 hertz signal approximately.
Yes, I saw
it can be. Yeah, and I think maybe this is what they're pointing out when they say there's a difference for erectile function. They're showing a difference between two people. They're saying that in one there is no reactivity like this, but on the other one there is something that's going on. I don't know if you should always put on your x-axis the units, because I suppose they are seconds.
Yeah, that program is made by like a bachelor student. So I don't know how about now.
But even in your presentation, you can always add in PowerPoint the units, right?
Yes, thank you.
Yeah. But if you go back to that that one where you say you don't know what the difference between the two graphs,
Yes.
can you go back to that?
Well, then that is not my problem. It's from the. Is it this one?
There are two graphs, so there's maybe the one above it and this one. Yeah. So if that is seconds on the bottom or not?
Yeah, second on. No, this is one person, but before the treatment and after the treatment.
Yes. But in the x-axis, this is
Yes.
minutes and seconds, or what?
I don't know. Let's see.
Go with it.
It's minutes. Yes. Yeah, it's minutes.
Minutes. Okay. So
it's from the 44 seconds to this time, and this one is from 18 minutes to that.
okay, but you can see this rhythm is
Yes,
more or less
yes.
once every 10
I
seconds.
saw it.
So it's relating to endothelial function, I think.
Yes.
And so, for example, in diabetes, you will not see this function, because their endothelial function is impaired. But in a healthy individual, in a resting state, should usually see this
Yes.
kind of activity. So I think that should be quite interesting.
Thank you.
Check.
Actually, you solved the problem.
Yeah. And these are inverted. These pulses are inverted because you are looking at the optical absorption.
Yes.
So when you have more blood, you have more absorption.
Yes.
You have less. You have less light,
Yes.
and you have more light when you have less blood.
Yes, it's inverted. But what do you think? The reflected one and the transmitted one also inverted, right? These two.
They're both inverted. Yeah.
Yeah.
But in the reflection, you need to be careful about the separation distance between the source and detector.
Yes. I used it to hear it. Nothing can be detected. Only on fingers. Only on finger.
Well, the source and detector need to be within a few millimeters
Yes.
of each other, and the optimum is about 4 or 5 millimeters separation. Depends on the wavelength. So that should give you the best signal.
Thank you.
That is what you want to do.
Thank you so much. Okay.